Good morning everyone, my name is Jason Parilla Bermejo. My topic is all about Theorem 4.10, Basis and Linear Independence. If S, V1, V2, and Vn is a basis for a vector space V, then every set containing more than n vectors is V is linearly dependent. Example, linearly dependent sets in R raised to 3 and P raised to 3. R raised to 3 has a basis consisting of 3 vectors, so the set S equals bracket open parenthesis 1 2 minus 1 close parenthesis open parenthesis 1 1 0 close parenthesis open parenthesis 2 3 0 close parenthesis open parenthesis 5 9 minus 1 close parenthesis bracket. B. P raised to 3 has a basis consisting of 4 vectors, so the set S equals bracket 1 and 1 plus x 1 minus x 1 plus x squared 1 minus x plus x squared bracket must be linearly dependent. Solution: Rn has the standard basis consisting of n vectors, so it follows from Theorem 4.10 that every set of vectors R raised to n containing more than n vectors must be linearly dependent. The next is Theorem 4.11, number of vectors in a basis. If a vector space V has one basis with n vectors, then every basis for V has n vectors. Example, spanning sets and bases. Use Theorem 4.11 to explain why each statement is true. A. The set S1 equals bracket open parenthesis 3 to 1 close parenthesis open parenthesis 7 negative 1 4 close parenthesis bracket is not a basis for R3. B. The set of S2 equals bracket 2 plus x squared negative 1 plus x to the third power 1 plus 3x minus 2x plus x raised to 2 is not a basis for P raised to 3. Solution: the standard basis for R raised to 3 S equals bracket open parenthesis 1 0 0 close parenthesis open parenthesis 0 1 0 close parenthesis open parenthesis 0 0 1 has 3 vectors and S1 has only 2 vectors. By Theorem 4.11, S1 cannot be a basis for R raised to 3. B. The standard basis for P raised to 3 S equals bracket 1 x squared x cubed bracket has 4 vectors. By Theorem 4.11, the set S2 has too many vectors to be a basis for P raised to 3. Definition of the dimension of a vector space. If a vector space has a basis consisting of n vectors, then the number n is the dimension of V denoted by dim open parenthesis V close parenthesis equals n. When V consists of the 0 vector alone, the dimension V is defined as 0. Example, finding the dimensions of subspaces. Find the dimension of each subspace R raised to 3. A. W equals DC minus DC. C and D are real numbers. B. W equals 2B, B0. B is a real number. Solution: A. By writing the representative vector DC minus DC as DC minus DC equals 0 CC plus D negative D 0 equals C open parenthesis 0 1 1 close parenthesis plus D open parenthesis D negative 1 and 0. You can see that W is spanned by the set S equals 0 1 1 1 negative 1 0. Using the techniques described in the preceding section, you can show that this set is linearly independent, so S is a basis for W and W is a two-dimensional subspace of R raised to 3. B. by writing the representative vector 2b b0 as b open parenthesis 2 1 0 close parenthesis, you can see that W is spanned by the set S equals 2 1 0. So W is a one-dimensional space of R raised to 3. Finding the dimension of a subspace. Find the dimensions of the subspace W of R raised to 4 spanned by S equals V1, V2, V3 equals negative 1, 2, 5, 0, 3, 0, 1, negative 2, negative 5, 4, 9, 2. Solution. Although W is spanned by the set S, S is not a basis for W because S is a linearly dependent set. Specifically, V3 can be written as V3 equals 2V1 minus V2. This means that W is spanned by the set of the other, and you can conclude that the dimension of W is 2. 4.12 Basis test in an n-dimensional space. Let V be a vector space of dimension n. 1. If S equals V1, V2, Vn is a linearly independent set of vectors in V, then S is a basis for V. If S equals V1, V2, Vn spans V, then S is a basis for V. Example. Testing a basis in an n-dimensional space. Show that the set of vectors is a basis for M5 and 1. 1, 0, 0, 0, 1, 0, 2, 1, 0, 0, 2, 0. S equals negative 1, 3, 2, 0, negative 1, 0, 3, negative 2, negative 1, 2, 3, 0. 4, 3, 5, negative 3, 4, negative 2. Solution. S has 5 vectors and dimensions of M5 times 1 is 5. So apply theorem 4.12 to verify that S is a basis by showing either that S is linearly independent of that S spans M5 times 1. To show that S is a linearly independent from the vector equation C1 V1 plus C2 V2 plus C3 V3 plus C4 V4 plus C5 V5 equals 0, which yields the linear system below. C1 equals 0. 2C1 plus C2 equals 0. Negative C1 plus 3C2 plus 2C3 equals 0. 3C1 minus 2C2 minus C3 plus 2C4 equals 0. 4C1 plus 3C2 plus 5C3 minus 3C4 minus 2C5 equals 0. This system has only the trivial solution, so S is linearly independent. By theorem 4.12, S is a basis for M5 times 1.